All right, so I want to make another video talking about refraction. Refraction is a really fun subject to talk about. It's a really fun subject to think about. The way that light propagates, the way that it changes direction, the way that it slows down. It's just a fascinating topic. There's so many things to think about when you're thinking about refraction, especially atmospheric refraction. But I wanted to just kind of take you through my thought process as we go through this. I know that I'm not an expert in refraction. I know that I'm not a scientist. I'm not on here trying to pretend to be a scientist, but I think a lot of times scientists overlook possibilities because they are so educated about the assumption that has already been made, and they assume that the assumption is fact, the way that it is. So it's not the case of flat earthers trying to be smarter than the scientific establishment. That's definitely not the case. But it is a case of thinking about things in an out of the box way and testing them. And that's what this is about. I can't tell you how many times that I've had an idea and I proved myself wrong when I tried to test the idea against my own ideas, right? It happens. And I don't think I'm wrong with refraction. And that's why I'm continuing to talk about it. I definitely do not want to accept the results of the first laser experiment that I did as far as what you would see with the sun or what that would do to light of distant objects or anything like that. A lot of it has to do with the container, the size of the container, the density of the solution. All of those things matter, right? And playing with it, I can get the light to bend up in my fish tank, right? And I have a big cylinder fish tank that I bought last night, which is horrible for this experiment, but you can get the light to do all sorts of cool, crazy things, reflecting and bouncing off the walls. One of the things I was thinking about is what would happen if I shine a light straight down, into the water. What way would it curve? What way is down, right? What way is down when that light is slowing? And I got some really interesting results with that. So this is fun. I'm not saying that I'm right and everybody else is wrong. I know that, there are different ways to look at things, and that's what I'm trying to show you is that there are different ways to actually view this. And the accepted reasoning for being able to see things from further than we should is that refraction is taking place. And refraction, regardless of how far over the horizon those things are, and that refraction would be the same angle from all of those objects. In the current understanding, refraction is causing all of those objects to look level even with the horizon, right? And what people are saying on a flat earth is, well, your entire field of view of the building that you're looking at would rise into the sky. And that's not the case. That would be a mirage, right? Because if I'm looking at refraction in the distance, I'm going to watch the horizon rise depending on the angle to the horizon, right? And usually I'm looking down at the horizon. And if you don't think so, if you're a globe proponent and you don't think that I'm looking down at the horizon, where's the drop, right? Because I don't really think I'm looking down at the horizon, but it appears that I am, right? I think we live on a flat earth and that the atmosphere is blocking and redirecting a lot of the light from the distant objects that we should be seeing. And yes, we can see further than we should. There's no doubt about that, right? But the atmosphere is the reason why we can't see forever. So what we're doing is we're taking it and we're flipping it on its head. And I want to think about this. So if I'm an observer and I'm standing in front of a tall building, this is a 3-story building. So if I was standing here looking at the 3-story building, I would be looking up at the top of the building. And because I'm looking up and the photons are traveling in a straight line to my eye, refraction over this distance it's not going to happen, right? And if it does happen, if there is a change in medium or in density over this distance, it's going to be imperceivable to my eye because I'm standing so close to the object, right? So when we're in close vicinity of an object, we can just say, okay, the photons that are being emitted are reflecting straight to my eye. Now, there are photons being emitted in all directions from the corner that I'm looking at, right? So if I take that beam of light and I, twist it the other way, if I was up here looking at the building, I would get photons that are reflecting this way, right? But these photons, even with the small angle of refraction, they're never going to hit the ground. they're going to keep going and going and going and going. The only photons that are going to hit the ground are ones that are coming off of the building in a straight line or at this rate, right? Kind of down towards the surface. These would be perceivable on the ground. So where am I going to be able to be to see any of the photons reflected off of the front of the building? Well, I'm going to have to be somewhere inside of the building's view, right? I'm going to have to be somewhere inside of this box where the photons traveling from this way. I can look down and I can see the perspective of the building from here. I can look straight and I can see the perspective of the building in a straight line. I can look here, but I would never be able to look from this angle, right? And it doesn't matter how far away I am, I'm never going to get the perspective of the building from that angle, right? We imagine photons, shining off in all directions. Well, it's a diffuse object. And if I have photons shining off this way into the sky, for one, if refraction is affecting that, it's going to continue to move into the sky. You're talking about a very small angle change, but any angle change of a photon traveling in a straight line from the face of the building that I'm looking at, if refraction is playing on that photon is going to be curved down at a downward trajectory, right? And the further I am away from that building, the less likely it is that the photons are going to hit my eye if refraction is at play, because all of the photons are bouncing into the ground. And they're not bouncing into the ground and bouncing off of the ground. If the photons were bouncing off of the ground, I would see the building here, right? But if the photons are hitting the ground because they are at a downward angle based on my straight view, then I'm not ever going to see the building, right? Now, the bottom of the building, in this case, is going to disappear before the top of the building, right? With standard refraction, we cannot assume a ball if we're going to assume a flat surface. And that's what you have to do. If you're going to experiment thinking, what would it look like on a flat Earth? You're going to have to assume a flat surface. And if we're living on a flat surface and there's no convexity, this light ray isn't going to bend over a hill, right? It's not going to bend over a hill and hit my eye straight. But a photon has to hit my eye straight. It's got to hit my eye in a straight line or I'm not going to be able to see it. If I'm not looking at something, I can't see it. And that brings me to the next part of this discussion that I think is just really amazing. It's really cool to think about. And that is scale, right? So right now we have the building really, really big and really, really close to the observer. And if the building is close to the observer, you're not going to have a lot of effect with refraction. However, if I am looking up at the top of the building, because of the angle of light that's coming down and hitting my eyes, the building is going to look a little bit higher than it actually is. But the entire surface is going to blend in with the building. If anything, you're going to get a little bit of a stretching of the entire image, right? If you're looking up at the building, it might look a little bit taller, but it would really be imperceivable from a close distance. Now, the further I move away from the building, the smaller the building is going to get. And here's what's a trip, right? So if light is traveling in a straight line from the building, regardless of the angular size of the building should be straight in front of me, right? Even on a globe. If the building is, because by the time the building goes, especially a 3-story building, by the time it, starts to obscure, it's still relatively close. You're within 10, 15 miles of that building before that building is completely obscured to your point of view. So even with a smaller building like this, the photons should be way higher than what they are if photons are indeed traveling in a straight line. This is where it gets, it's unperceivable to me. And I know that there are mathematical equations and things like that, but let's just think about it logically. Okay, if I'm looking at a building from 30 miles away, 20 miles away, like over a big body of water, the building is not going to be up here. The building is going to be down here on the horizon, right? I'm going to have to look down Remember, I mean, if we're looking 30 miles, we're looking down, we're not looking up, correct? Okay, so if I'm looking down at this building that is on the horizon, then the photons are coming out of the building in a straight line and refracting slowly at a downward angle of 0.5 degrees or whatever it is. Am I ever going to get light from up here on the building? Are the photons going to do this? Are they going to do this up here and then start to curve back down to my eye? No. I'm going to have to look down at the building, right? And that's what doesn't make sense about light. Because if I take a theodolite and I make the measurement of where that building is on the horizon, the building isn't visible unless I have infrared or something like that. I'm not going to be able to see the building. And the building shouldn't be visible on a curved surface, but it is, right? Remember, we're thinking about it on a flat surface. We're not thinking about it on a curved surface. And that's where all the globe proponents who are arguing with me about this are getting confused. Now, again, let's think about it. If light is traveling in straight lines away from this building that I have to look down to see, even with a theodolite, then are the photons from that building not eventually going to hit the ground and obscure the building from the bottom up? Very simple. And that is what people, again, it's like equinox. People say, well, the sun's rays are parallel to the earth. The reason why the earth looks curved is because the sun's rays are parallel to the earth. They're shining from an 865,000 mile diameter sun. But what if that is not the case? Right? And people say, well, we measured it. We know, we blah, blah. No. The government doesn't tell you everything. Right? Look at what's going on now. There are things that the government doesn't have to tell you that you don't need to know, and you will never know as a civilian, even as a top government scientist. And if you're at the very top where you do know, you're not telling anybody because you have your reasons for keeping it a secret, and it's nobody else's business because governments think that they rule the world, right? A government institution, a power of authority, a power seat of authority is going to think, well, hey, we're in control of the people. They don't have to tell you everything about the model. Just because you see data from a satellite doesn't mean that the data is accurate, and it doesn't mean there's even a satellite. And I don't deny low Earth orbit. I don't deny that there are satellites up there. I look at them with my telescope. I see the ISS with my naked eye every time it goes over my head. So I know that there are satellites. I'm not going to deny that, but the satellites may work a different way, right? And the information that we're getting may not be accurate as far as what the satellite is actually detecting. And that would not be that hard to pull off, especially with today's technology. And look at the differences in the images. Go back to 1960s NASA footage and go to the current NASA footage and look at how much space has changed, right? Look at the pictures of the stars in space from NASA, from the spaceships that NASA had. Remember back then they could photograph the stars and the moon and everything else with the light of the earth. Go look at those images, right? And compare those images to the images that you see today. Clearly those images were edited, right? Anybody with a modern eye can look at those early 1960s images and say, hey, wait a minute, that's crazy. That's not real. You know, so what changed with the 80s? Because I can look at 80s footage and be like, dude, that looks like that looks so fake, right? And it does. And then you look at modern footage, and modern footage special effects are getting a lot better, right? So the space footage obviously is looking better and better as well. And like I said, I'm not saying they can't take space footage, okay? But it's not always what it seems to be, and you can change a lot of things with the lens, and there are a lot of things. So again, if I'm looking at a building in the distance, I'm not looking up to see the photons, even though the photons are technically above me, right? I'm not looking up on a globe. If I'm 1 mile down the road from a 60-foot tree, that 60-foot tree is going to be level to my eye, talking about the top of the tree, maybe a little bit above. But if I move 10 miles down the road, that tree is going to be blended in with the horizon. And at 10 miles, I've got to look down. I'm 6 foot tall. So if I want to see the horizon on a flat surface or on a globe, my eyes are going to have to look down. To see that building, I'm going to have to look down to see it, right? So The way that we're fitting this into the model that we're going to be overviewing is that probability has everything to do with scale, right? It's not a function of the way light behaves with an object that's farther away. It's the fact that the object is further away. And if an object is further away, I have a tin can right here on my desk that a Mountain Dew can that I'm lifting up and drinking every once in a while. But the further away this Mountain Dew can is from me, the smaller it is, because the less I can interact with it, right? The less probability there is. So if I put this Mountain Dew can 20 foot away in a post and I shoot it with a BB gun, right? My probability of hitting that, although, it's pretty good, not terrible, but not really good, and the further I move that Mountain Dew can away, now I pull out the 22, now I pull out the rifle, the long rifle or whatever it is, the further I move that away, the smaller it gets because the less probability there is that I'm going to be able to interact with this object at all. Until eventually the object just disappears into the background because there's absolutely no probability, right? And a larger object is going to give me a greater probability of being able to interact with it. If I'm looking at a big 60-foot tall tree, I can hug the tree, I can climb the tree, I can put a swing in the tree, I can do all these things to the tree. But once I step back, again, the things that I can do to that tree are a lot less, right? I could probably lasso a rope around it, or I could, shoot it with something, or I could throw something at it, or I could visually represent it in a picture or a painting if I'm standing close enough. But the further away I get, the perspective of that tree is changing because all of the possibilities are changing, or the probabilities. What are the probabilities that based on anything, I'm going to interact with the tree that's 20 foot away from me, right? It's there. But what about a tree that's a mile away from me when you have thousands of other trees? Right? What about a tree that's 2 miles away or 10 miles away? Could I see a tree that's 10 miles away? And is there anything that I could do in my physical reality, unless I move my perspective forward with like a missile, is there anything that I can do to interact with the tree? And the closer that missile gets to the tree, see, I know the trajectory of the tree. So I can fire the missile at the tree, and the closer it gets to the tree, the more visible that tree becomes. And the greater the probability is that I'm going to be able to hit the tree. Even just firing in the same general direction as the tree, the probability is going to increase because of all of the available things that I have that allow me to interact with the tree. So the point is that perspective and scale and all of these things we're viewing in the physical world, to me, it works a lot more like a render. But I want to continue having the conversation, and I want to see what you guys think. So what are your thoughts?